How's it going, everyone? In this video, we're going to talk about how to calculate probabilities using the normal distribution. If your random variable follows the normal distribution, how to calculate the probability of observing something within a certain range. So, just as a recap, the normal distribution is defined by your mean value and your standard deviation. The mean value determines the location of the peak of your normal distribution. Your standard deviation determines the width of your normal distribution. And for continuous random variables, the probability of being within a certain range, the probability of observing a value within a certain range, is the area under the curve within that range. So, for example, let's say we have a normally distributed random variable representing grades. And let's say the peak is located at the mean value of 65, and let's say the standard deviation happens to be equal to 10. So let's say we want to know, well, what is the probability of observing a value less than 50? Right? What's the probability that someone scored below 50 on this test? Well, that is going to be the area under the curve below the point x equals 50. Now, this is not exactly an easy shape to calculate the area of. But lucky for us, someone already calculated a bunch of areas under the curve for the normal distribution, and we can just go to that table and look up the areas that we need. That's the good news. The somewhat inconvenient, but somewhat convenient news is that this table exists for a very specific normal distribution, and that is a normal distribution with a mean value of 0 and a standard deviation of 1. Now, why such values for the mean value and the standard deviation? Well, because those are easy values to work with. 0, 3, -3. Right? So based on the empirical rule, pretty much all of the data is within 3 standard deviations of the mean. So if our standard deviation is 1, pretty much all of the data is between -3 and 3. So if the random variable you're working with happens to have a mean value of 0 and a standard deviation of 1, great, you can calculate all the probabilities you want using what's called the Ztable. Now, typically, the normal distribution of your random variable does not have a mean value of 0 and a standard deviation of 1, but you can do what's called a transformation. You can alter your data to make the mean value 0 and the standard deviation of 1 while maintaining the same shape of the distribution. It's like converting between Celsius and Fahrenheit. You can use different numerical scales to describe the same thing. So, if x represents values of your random variable, the z value, which is a transformed value, is going to be x minus the mean divided by the standard deviation. So whatever your random variable is that follows the normal distribution, if you create this random variable z based on this formula, the distribution of z will be a normal distribution with a mean value of 0 and a standard deviation of 1. And that distribution, that's called the standard normal distribution. So not just any normal distribution, the standard normal distribution has a mean value of 0 and a standard deviation of 1. So, for example, I'm going to pull up Excel for this example. Let's say these are our x values. And I'm just going to put in some random positive values here. So our mean value is certainly not going to be 0. Okay, let's calculate our mean. And we're also going to look at our standard deviation. So, I'm actually going to create some boundary lines here to make it easier. So our mean value is approximately 5. And our standard deviation, and actually let's go for the population standard deviation, is approximately 1.7. And I'm going to reduce the number of decimal places here so it's easier to look at. Now we create our z values, which are equal to x minus the mean, mu, divided by sigma. Okay, so what I'm going to do, I'm going to do x value minus the mean, and we're going to put dollar signs there so that Excel copies and pastes the formula correctly, divided by the standard deviation. If you're not familiar with Excel, you might not be sure why these commands do what they do, but there is a Excel tips playlist that you can look at. I'll put the links below this video so you'll know what all these things mean. Okay, so these right here are our z values. I'm going to add a few decimal places because it looks like a few of them are pretty close to 0. There we go. So it's like converting between Celsius and Fahrenheit. Our x value is 1, but on the z scale that's a negative 2.42. If our x value is 5 on the z scale, that's a negative 0.5. If our x value is 8 on the z scale, that's a 1.73. And if we look at the mean value and standard deviation of our z scale, you'll notice that the mean value is 0 and the standard deviation is 1. Because in that formula, when we subtract the mean value from our value of the random variable, that's what ensures a mean value of 0. Because we're subtracting the mean value from every single data point. And when we subtract that difference by the standard deviation, that's what ensures that we get a standard deviation of 1 for our z random variable. Now that z scale is very useful, not only because it gives us an easy mean and standard deviation to work with numerically, but also if you look at the z values, if the z value is negative, that means you're dealing with a data point that is less than the mean value. If the z value is positive, it means you're dealing with a data point that is more than the mean value. If the z value is close to 0, it means you're dealing with a data point that is very close to the mean value. In this case, 5 is, well, it is very close to the mean value because the mean value is 5.1. You'll also notice that pretty much, in this case actually all of our data points, are between negative 3 and 3, because as we expect with the normal distribution, based on the empirical rule, pretty much all of the data is within 3 standard deviations of the mean value. And if your mean value is 0 and your standard deviation is 1, within 3 standard deviations of the mean value means you're between negative 3 and 3. So with this, we can use what's called the Ztable. The Ztable looks like this, and it gives you the area under the curve below any z value. So here's how we do that. Let's go back here and create our example. So we have our normal distribution. With our mean value of 65 and our standard deviation of 10. And we want to know what's the probability of randomly selecting a value that is less than 50. Okay, well, 50 is somewhere along this scale, so we want to know this area under the curve. Well, the first thing that we're going to do is we're going to convert that x value, that cutoff, 50, we're going to convert it to the z scale. Okay, and that's step one, convert to the z scale. So, mu equals 65, oops, not 56, 65. Standard deviation is 10. Find the probability that x is less than 50. So step one, convert to the z scale. Okay, so z equals x minus mu divided by sigma. So our cutoff is 50, so that's 50 minus the mean value divided by our standard deviation, which is 10. So that's going to give us negative 15 divided by 10, which is negative 1.50. So we found our z value. Part 2, find the corresponding probability on the z-table. And the z-table gives us the probability of being below a certain value. So we're going to look up negative 1.50 on the z-table, and that is going to tell us the probability of being below negative 1.50. So the probability of z being less than negative 1.50, which is equal to the probability of x being less than 50, is whatever the z-table tells us. So let's go find negative 1.50. So the way the z-table works is you look up your value to the first decimal place in the first column. So negative 1.5 right here. And then the second decimal place, which in our case is 0, we look up in this column here. And then we match in that row. So we match up the row and the column, and we get the value 0.0668. 0.0668. 0.0668. So, if we want that in percent form, sure, 6.68%. That's just multiplying it by 100. So, if students write a test, the mean value is 65, that's the mean score, the standard deviation is 10, the probability that a student, randomly selected student, got less than 50 is 6.68. You can expect 6.68% of students scored below 50. Okay. Now, let's say we're asked, well, what's the probability that x is above 76? Okay, same test, but we want to know what's the probability that x is above 76. Okay, well, we do our step one. We find our z score, right? Z is x minus mu divided by sigma. So that's going to be 76 minus 65 divided by 10. Okay, so 76 minus 65 is 11 divided by 10. That gives us 1.10. So that's our z value. Step 2, we look that up on the z-table, which will tell us the probability of z being less than 1.10, which is equal to the probability of x being less than 76. So let's look that up, 1.10. So we go to our z-table, we look for positive 1.1, second decimal point is 0, match that up, we have 0.8643. 0.8643. 0.8643. Or in percent form, 86.43%. But here's the problem. This is the probability of x being below 76. We wanted the probability of x being above 76. So, that's not what we're looking for. But we can use it to get what we're looking for. Because the probability of x being above 76, well, that's just the probability of x not being below 76, right? Because remember, it's a continuous random variable, so you can't have x being equal to 76. So 1 minus the probability of x being below 76. So 1 minus 0.8643, and that's going to give you 0.1377, or 13.77%. So the probability of x being above 76 is 0.1377, or 13.77%. So even though the Z-table gives you the probability of being below a certain value, if you want the probability of being above that value, just subtract that probability from 1, and you get your answer. Now you might be thinking, oh, hold on, but it is possible to get 76 on a test, right? Yeah, it is possible, and representing our test score as a continuous random variable is an approximation. Representing it as a normal distribution is an approximation. Chances are your test scores won't exactly follow the normal distribution, but it's an approximation that is very, very useful because so many things in nature approximately follow the normal distribution. And there's also many, many things in nature that will exactly approach the normal distribution, which makes it such a powerful tool. And you could look up the set of videos on the central limit theorem if you're interested in that. And again, that's also in the statistics lectures playlist. So let's do another example. And let's change our numbers. Let's say our mean value, let's say we're looking at hours of sleep. Okay, and let's say you study some population and the mean value is 7.5 and the standard deviation is 0.8. And we want to know what's the probability that someone gets between 6 and 8 hours of sleep. Okay, so we're not looking for the probability of being above a value or below a value. We're looking for the probability of being between two values. Okay, so we can draw our normal distribution, right? And there's our 7.5 at the peak. That's our mean value. Okay, and there's our 8 somewhere above, and there's our 6 somewhere below. And we want to know the probability of being between 6 and 8. Okay, so we want to know this area under the curve. Well, we've got two boundaries here for x, so we've actually got two different x values to convert to z values. So we're going to have z1, which is equal to x1 minus mu over sigma, or 6 minus 7.5 over 0.8. Okay, so 6 minus 7.5 is negative 1.5. And when we divide that by 0.8, that gives us a negative 1.875. Technically, we're going to round that up to 1.88 just for the sake of this video, because the Z-table does give you up to 2 decimal places. So we'll go negative 1.88. Okay. And for our second z value, we have z2, which is equal to x2 minus mu, which is 8 minus 7.5. And of course, we're dividing by sigma in both cases. All right. So 8 minus 7.5 is going to give us 0.5. And when we divide that by 0.8, which is our sigma, we get 0.63 if we round to 2 decimal places. So we have two Z values, right? We have negative 1.88 and positive 0.63. So if we look up negative 1.88 on the Z table, that's going to give us the probability of Z being less than negative 1.88, which is the same as the probability of X being less than 6. And the value that we get, if we look up negative 1.88, so we go to our Z table, there's negative 1.8, then we find our second decimal place here in that top row, 0.08, and we match those up, and we have 0.0301. 0.0301. 0.0301. And that is equal to this region right here. Right? That's the probability of being below 6. I'm going to put a red box there to signify that. Okay, now if we look up our second Z value, the probability of Z being less than 0.63, which is the same as the probability of X being less than 8. Well, what does that give us? Let's look up 0.63 on the Z table. So there's 0.6. There's our second decimal point, 3. So we match those up. And we have 0.7357. 0.7357. 0.7357. And that is this area right here. It's the area under the curve that is less than 8. Well, neither of those areas is the one we're looking for. We're not looking for the blue shaded region. We're not looking for the red shaded region. We're looking for the black shaded region. But notice if you take that blue shaded region and you subtract the red shaded region, what are you doing? You're cutting off that tail. And what you're left with is the black shaded region that we are looking for. So to find the probability of X being between 6 and 8, you just take the larger probability and subtract the smaller probability. So the probability that X is between 6 and 8, which is the same as the probability that Z is between negative 1.88 and positive 0.63, that's just going to be 0.7357 minus 0.0301. And what that gives us, 0.7357 minus 0.0301, that gives us 0.7056, or in percent form, 70.56%. So, if you've got a study that shows that the mean value for hours of sleep for some group is 7.5 and the standard deviation is 0.8, and you assume that this random variable follows a normal distribution, you can conclude that 70.65% of the population you're interested in gets between 6 and 8 hours of sleep. And that's how you calculate probabilities using the normal distribution. Now, sometimes a situation could be in reverse. So a situation could be as follows, where, let's say, same situation, we have our mean value 7.5, our standard deviation 0.8, but we're not looking for a probability based on a certain range. We're looking for defining a range based on a probability. So let's say we want to know how much sleep do the top 10% of people get in terms of hours? Now that might be slightly awkward wording, but so we want to know, okay, of all the people, who are those top 10% who get the most sleep? Okay, how much sleep do they get? Those 10% who get the most sleep. So here, we already have a probability. What we're looking for is an x value. So let me draw that out. There's our normal distribution. There's our mean value, 7.5. And there's our 10% right there. Our top 10%, 0.10, which tells us the not shaded region is 0.90. And there's this cutoff here. We want to know what that value is. What's that value for which we can say 10% of the population get more hours of sleep than this, and 90% get less? That's what we're looking for. So what we did before in the examples is that we started off with an x value, we converted to a z value, and then we got a probability. In this case here, we're starting with a probability, and we want to get the corresponding z value and then convert that to an x value. And the probability we're starting with isn't 10%, it's 90%. It's 0.9000. Because if we're using the z-table, we want to know the probability of being below a certain value. The z-table only tells us the probability of being below a certain value. If we're looking for the top 10%, that cutoff, that's the same as looking for the cutoff for the bottom 90%. So we're going to go to the z value, and we're not going to look at the top row or the leftmost column. We're going to look in the middle where the probabilities are, and we're going to look for the value closest to 0.9000. So here we are. Where's that value closest to 0.9000? We look and look, and there it is. Of all the probabilities on the z-table, the closest one to 0.9000 is 0.8993. That's the closest one. Okay? So what z value does that correspond to? 1.2, and the second decimal point is 8. 1.28. That's the corresponding z value. So we know that this z value here is 1.28. So what's the x value? Well, we have our formula that tells us the z value based on the x value. And if we rearrange that formula to solve for x, the most stereotypical mathematical thing to do, well, multiply both sides by sigma. You get z sigma equals x minus mu. And then bring mu to the other side, or add mu to both sides. You get mu plus z sigma equals x. That's how you get your x value. Okay? These two formulas is actually the exact same formula, just one is arranged to solve for z, the other is arranged to solve for x. So, our x value is going to be mu, that's 7.5, plus z, which we found to be 1.28 on our z table right here, 1.28. Plus 1.28 times sigma, our standard deviation was 0.8, right? Standard deviation right here. And then we just do that calculation. So 7.5 plus 1.28 times 0.8 is 1.024, 1.024, 7.5 plus 1.024 is 8.52. 8.52. or we can just say 8.5 because it's easier to think of that when we're talking about hours of sleep. So if your study shows that on average people get 7.5 hours of sleep with a standard deviation of 0.8, and you assume that hours of sleep follows a normal distribution, you can conclude that 10% of the population gets more than 8.5 hours of sleep, and 90% therefore gets less than 8.5 hours of sleep. And those are the kind of questions that you can ask and answer dealing with the normal distribution and the Z-table. So I hope that helps, and until next time.